All right, welcome back. Thanks for braving through the snow. I almost didn't make it here today, so let's begin and learn basic scheduling. So, there's an important two types of resources. Everyone still talks, okay, great. So, yeah. You still got 10 minutes, what? Okay, so today we're talking about basic scheduling. So there's two main types of resources here. There's something called preemptible resources and non-preemptible resources. So the major difference between them is preemptible resources can be taken away and used for something else. So like a CPU is an example of a preemptible resource. I can give your application the CPU. Yeah. Oh, for the class, it kind of works, but not really. It's at max. So I guess I'll have to complain at tech after. So yeah, so a preemptible resource is just something that can be taken away at any time, like CPU, so your application can go execute, do whatever, and then the kernel can go ahead, take away the CPU from you, and start running another application. So preemptible resources are typically shared through scheduling, and an example of a non-preemptible resource is just anything that cannot be taken away without acknowledgement. So it's something that's given to you, and you get to use it, you don't have to share it. So like disk space would be an example of a non-preemptible resource. So you get some disk space, you either use it or you don't, it's not taken away from you. So non-preemptible resources are shared through allocations and deallocations, and memory would be another example of this. And for note, if you get into like really high performance computing, well, you can actually allocate a CPU and deallocate a CPU, but in normal circumstances, it's just a preemptible resource that the kernel controls. So there's two things. There is a dispatcher and a scheduler that kind of work together. A dispatcher is the like low-level mechanism that is actually responsible for context switching. And the scheduler is the high-level policy that decides what processes run when and where. So the scheduler just runs whenever a process changes state. So first we'll consider a non-preemptible process. So if a process is executing, it can't be, it doesn't stop executing. So it just runs until completion. So in this case, our scheduler is pretty simple. We just have to make a decision when a process terminates and I need to put something else on the CPU to run. So this is preemptive. And again, preemptive means the operating system runs the scheduler at its own will. So if you do like uname-v and your kernel, that's one of the things it will tell you. It will say preempt in it, and that means that it's a kernel that maintains control and will pause your processes and swap them in and out. They don't just run until completion. So there's a few metrics when we discuss scheduling, and some of them are kind of at odds with each other. So we ideally want to minimize something called waiting time and response time. So you don't want to have a process just sitting there doing nothing. You want it to actually execute at some time, and you want it to actually, perform some useful work for you. So ideally, you would like to minimize that. You also want to maximize CPU utilization. You don't want a CPU idle. If you only have a single CPU, that's not too difficult of a task, but it becomes harder and harder the more CPUs you have. So if you have, 128 cores or something like that, then that job might be significantly more difficult than if you just had a handful. Then another thing we want to do is maximize throughput. So we want to complete as many processes as possible. And the last one, which is kind of at odds with all the other ones, is fairness. So you want to give each process, approximately the same percentage of the CPU if you can help it. So first one is the most obvious scheduling strategy, and this is what happens if you go, to McDonald's or something like that. It's just first come, first serve. And this is actually a valid algorithm. So it's the most basic form of scheduling. First process that comes in, you just form a line essentially and say you get the CPU, and then you store the processes in that line in FIFO order, so that's first in, first out, and whatever order they arrive in is the order they execute in, which isn't like a very compelling algorithm, but hey, we'll see this for a bunch of different questions. First come, first serve is typically the first thing you think about, and it's like a really easy thing to implement. So we'll go through a bunch of schedulers today, and they'll all be represented by Gantt charts, and we'll use the same example today, but fudge the numbers a little bit. So we'll consider 4 processes, P1 to P4, and then their arrival time is when they want to start executing, so when you would start them. And then the burst time is just another way of saying that's how long they actually will execute on a CPU for. And to simplify everything, we just argue it in time units, where the smallest time unit is just 1, so you can't do like half a time unit or something like that. So all of them arrive at the same instant at time 0, so we'll assume some arrival order between them, and we'll just assume that it goes P1, P2, P3, P4. So if you do that, and you do first come, first serve, our scheduler looks something like this. At time 0, every process we could execute, and we just pick the first one that arrived, which is P1, and it executes for 7 time units. So in this case, we're assuming non-preemptible things. So as soon as we pick it, it runs until it's done. So here, P1 would run from 0 all the way to 7, which would be 7 of those boxes, and then it's done. So as soon as it's done, we have another decision to make. We need to schedule another process. In this case, it would be P2 because it was the second one in line, and it runs for 4 time units. So 1, 2, 3, 4. Now at time equals 11, we have to schedule something else. P3 was the next. It's 1 time unit. We schedule it. 12, make another decision. There's only one thing left. So P4 goes for the last 4 time units. So any questions about that simple scheduler or like the way it's presented? Yep.
Sorry, how does tie breaking work?
So tie breaking would work, in this case, tie breaking works because I gave an order here. So everything looks like a tie, but you'll always be given an explicit, like arrival order, to essentially break the ties. So this looks like a tie, but in this case, you'd always be taking, what microsecond, it does faster. So in this case, if we compute the average waiting time for each process, we just add together how long it's waiting for, and then just divide it by 4. So they all are ready to execute at time equals 0. P1 waits 0 time units until it executes because it executed immediately. So P1 waits for 0 time units. P2 waited for 7 because it had to wait for P2 to be done. P3 waited for 11 because it needed to wait for P1 and P2 to be done. Then finally P4 needed to wait 12 time units because it needed to wait for the first 3 to finish. So our average waiting time, simple calculation, it would just be 12 plus 11 plus 7 divided by 4, since there's 4 processes, which I think, if my math is right, that's like 7 time units of average waiting time. So let's take that number 7 and have it in our head, and we'll go back to your question. So this looks like it's a tie, but we'll just assume a different arrival order at that time instant, so there's actually no ties. And if we do the same schedule again, well, we put P3 first, then P2, then P4, then P1. Now, in this case, if we calculate the average waiting time, well, it's a bit different. So P1, how long did it wait? Well, P1 waited for 9 time units because it had to wait for P3, P2, and P4. Then P2 only had to wait for 1 time unit. P3 waited for 0 time units. And then P4 waited for 5 time units. So our average waiting time now is 0 plus 1 plus 5 plus 9. So divided by 4, which is like 3.75. So just based off that order, without changing anything, our average waiting time essentially went down by half. and we just kind of got the luck of a draw. So this kind of gives us an intuition that this is like really, really inconsistent and probably a bad idea, and we can probably do something smarter. So the smarter way and the kind of most provably optimal thing to do is, instead of first come first serve, well, in order to minimize waiting time, I'll just schedule the job with the shortest burst time first and still assume no preemption. So if a process hasn't come in yet, I can't schedule it. So in this time, this is the example we'll use for the rest of the lecture, that the arrival time actually has different times, so there's no ties. So that's the only change here. So now if we do shortest job first, well, at time 0 now, only process 1 was requested to start, so we have no choice but to choose process 1. So we choose process 1, and it will execute until it's done at 7 time units, because again, no preemption yet. And while it's executing at time 2, P2 wants to execute, but it can't. Time 4, P4 wants to execute, but it can't. And then at time 5, P4 wants to execute, but it can't. So by the time it finishes, P1 finishes at time 7, we have 3 processes waiting. So we have P2, or P3, P2, and P4. So we'll just take the shortest job first, which is P3. And then between P2 and P4, there's a tie. So in the case of a tie of shortest, of like burst time, you would just take whatever arrived first. So in this case, our order we'd want to execute things at time 7 is P3, then P2, then P4. So after knowing that, we would just execute P3 for its 1 time unit. Then at T8, when it's done, we execute P2, then P3. So any questions about that? So now we can get our average waiting time, which will be a bit different because not all processes started at time 0. So for P1, well, it's waited around for 0 time units. It came in at 0 and it started executing at 0, so it didn't wait for anything. Then everything else gets shifted a bit. So P2 actually waited for 6 time units because it arrived at 2 and then didn't execute to 8. So 8 minus 2 is 6, or you could count the boxes if you want to. So it waited around for 6 time units. Then P3, it arrived at time 4, didn't execute to 7, so it waited around for 3 time units. And then P4 came in at 5 and didn't execute till 12, so it waited around for 7 time units. Yep.
How do we know the burst time in advance?
So that's a good question of how do we know the burst time in advance? Because you just kind of start a program and you don't know. So this is kind of, you analyze this after the fact. So when you're actually doing real scheduling, you will not know the burst time, but this is a way to evaluate things, after the fact. So that's a good observation because in real life, you're not going to know the burst time. But now, there's some research where you could, perhaps use some AI models and try and predict some burst time. But, if you're wrong, you might be really worse off than, if you just kind of have a more general policy. So in this case, our average waiting time would be 4. So if we just do the math on that. So yeah, going into that, not practical. It's provably optimal to minimize average wait time. But again, like you just pointed out, you don't know the burst times of each process. So that kind of puts a wrench in our plans right there. You could, use the past to predict future executions, AI, whatever. But this has some fundamental problem of something called starvation, where the really long jobs might not ever execute. So if you constantly get little short jobs and you favor them, then your CPU is only ever going to execute little short jobs, and the long ones will never execute. And being in a situation where a process can never execute is just starvation. So it doesn't have a chance to get any resources. So we also could have a little tweak to it. We could add preemptions to it. So shortest remaining time first is just the tweak to shortest job first, where things can get preempted. So it's still the same rules, except that we can interrupt any process that's running if a shorter one comes in. So again, we're just assuming the minimum execution time is 1 time unit, and this also provably optimizes the average waiting time and minimizes it as much as possible. So with the same setup here, well, it's going to be a bit different. So at time 0, there's only P1, so it would come, execute, and then at P2, now we have preemptions. So at time 2, P2 is able to execute, and it has a burst time of 4, and what is remaining left on process 1 is, well, it wants to run for 7, it's run for 2 time units now, so it has 5 left, and P2 has 4 left, so P2 has the shortest remaining time left, so you just schedule P2 to run instantly. So P2 would get scheduled to run, it executes for 2 time units, and then P3 comes in. So P2 has 2 time units remaining, it wants 4, it's executed for 2, and then P3 has 1 time unit it wants to execute for, which is shorter than everything remaining. So we would shove out process 2, put in process 3, and then process 3 executes for its 1 time unit, and then process 4 comes in. In this case, there's no tie. Process 2 has 2 time units remaining. Process 4 now has 4 time units remaining, and process 1 has 5 time units. So we'd pick process 2, runs for 2 time units, and then process 4 would go next, run for its 4 time units, and then then at time 11, process 1 would end. So yeah, shortest remaining time first still has problems with starvation. In fact, it gets a little worse. So our P1 actually executed to completion when we didn't have preemptions, but now if you have preemptions, you might tease it a little bit. It gets to run initially, and then you kick it away, and then it never runs again. So yeah, so this has the same starvation problems. So in this case, if we do our average waiting time, we have little gaps here that we have to account for. So average waiting time becomes a bit more of a problem. So in this case, P1 waited for 9 time units. That's 9 consecutive time units it wasn't executing for. And then P2, well, here it didn't have to wait any time. It started executing instantly, but before it was done, it had to wait 1 time unit while P3 was executing. So it waited for 1 time unit. P3 waited for 0 because it came in at 4 and executed immediately. And then finally, P4 waited for 2 time units, so these 2 time units. So a shorter way to get those, if there's bigger gaps or you don't want to like count the boxes or anything, you can just take the number from when that process finishes and then subtract that from when it started. So in this case, P4 finished at 11 and started at 5. So in total, the total time it was there was 6 time units. And if you subtract out the burst time, the thing you're left with is its waiting time. So it was there a total of 6 time units. It executed for 4 of those, so it waited for 2. So that's another thing you can do if you want to be quicker at it. So in this case, our average waiting time goes down a little bit from the case where we had no preemptions to preemptions. So now our average waiting time is 3 instead of 4. And that was mostly our intuition is mostly because we essentially kicked out P1 early. All right, so hopefully this is fairly straightforward, less confusing than all the forking and processes and things. So this is as tricky as it's going to get today. Yep.
When you're switching processes, like midway through execution,
Yep.
you still have to, are you loading it out of memory, or could you have like a whole bunch of, start a whole bunch of long tasks and just kind of gradually fill up your memory because short tasks come in every so often?
So the question is, when I switch tasks, like what am I wasting or what?
Like, do you still keep information about the process in memory?
Okay, yeah, so the question is essentially, when I'm switching between processes, is that process still in memory or what happens with it? So we'll get into the mechanics later, but realistically, when you switch them, you're switching like register values, like the program counter and stuff, and all that memory is going to exist. And when we get into virtual memory, we'll see how you don't do anything and they just can't use each other's memory anymore, and you get some protection. But we'll get into that after we get into virtual memory. Okay, so this is the last most complicated algorithm we'll get in today, and it also has some intuition, so it's round robin. So far things have not been fair. So, you know, if you have siblings, your parents might have done the fair thing. It's like, oh, you have to share a toy, so you each get, 5 minutes with it, and you have to pass it around. So round robin is essentially exactly that. So if you want to be fair, round robin. So the operating system will divide the execution into time slices, which has a fancy word called quanta. And then an individual time slice is just called a quantum. So that's like the smallest unit of time. So what we do to implement round robin is you still use a FIFO, but you kick things in and out. So you have a FIFO queue of processes similar to first come, first serve. And then based off your time slice, at the end of the time slice, that process that's currently executing just goes to the back of the line. So it just goes right back to the line. So any intuition about that quantum length, like the length of the time slice? So is there any practical considerations I should have if I'm actually selecting this value? Yep.
Like a clock cycle?
A clock cycle? So if I just do it too fast? So you'd have to do it at least in a clock cycle to be able to like change values or something like that, but you couldn't do much work. So if it was way too short, you couldn't even have enough time to switch processes. So nothing will happen then. Okay, yeah.
Is there overhead with switching processes?
Yep, so there's going to be some overhead with switching processes, so you probably don't want it too fast. And yeah, there's another one back there. Yeah, it should be longer than the switching time. What about if it's really big? So what about if the time slice is longer than any process takes to execute? Yeah.
And you just have first come, first serve?
Yeah, then it's just first come, first serve again, and then we have all the same problems again. So we kind of need to have a fine balance. We don't want it too fast, otherwise we're going to waste a lot of time just switching back and forth because that can't happen instantly. And if it's too long, it's just first come, first serve, which is decidedly not fair, right? If you have to share something with your sibling, but you get to have it for 18 years, well, then, you're all good if you're the first sibling. So we'll try and illustrate this too by showing different quantum lengths for the same schedule we've been arguing about so far. So here, I'll go through it real quick. So these are kind of like exam-ish questions. So here's our arrival times. We have a quantum length of 3 units, or a time slice, whatever you want to call it. So our time slice is 3. So when we make our scheduling decision, well, at time 0, P1 arrives. There's nothing else to schedule. So it would run for its time slice of 3 time units. So we can fill it in P1, P1, P1. And then at the bottom of every time instant there, I'm going to draw a queue whenever it changes. So initially, we would have P1 come in the queue, and then we have to decide what to execute. There's no other choice. We'd execute P1. Then at time 2, our empty queue would get P2 added to it. So the next time unit, we have something else to execute. Now, when P1's done its time slice at time 3, it would get added to the back of the queue. So at time 3, our queue would look like P2, then P1. So you just pick whatever is at the front of the queue for our next scheduling decision. And here, time slice again in 3 time units. So P1 or P2 would execute 1, 2, 3. So it would execute for its quanta, time slice, whatever you want to call it, of 3 time units. And during that time, some things happened. So at time 4, P3 arrived. So P1 would have been at the front of the queue because we took P2 off, and then we would have added P3 at the back. Then when P4 came in at time 5, well, P1 was still at the front of the queue, then P3 was next, and then P4. So then we go at time 6. Well, that's when P2 is done executing. It still has some more time it would like to execute, so it just gets added to the back of the queue. So now our queue looks like P1, P3, P4, then P2, which got kicked off at the back. So now we have everything in our queue. We just take it off in order. So P1 is next. So P1 would execute for its time slice of 3 time units. And it would fill up that whole slice because, it wants to execute for 7, and right now it's only at 6. So it would execute for its time slice of 3, and then get thrown to the back of the queue. So now we have P3, P4, P2, and now P1 is at the back. So now we just pick off the next process to run. It would be P3. So P3, P3, P3. Now it's done its time slice. Now our queue looks like P4, P2, P1, P3. Yep.
Wouldn't P3 only run for like one time zone?
Whoops, yep. I jumped the gun. So yes, sorry. P3, its burst time is only 1, so yeah, it wouldn't use its whole time slice. So thank you. Thank you. So P3 only executes for 1 time unit, and it's done. So if it's done, it'll just be kicked off, it executed, it's done, and we just pick off the next thing in the queue. So you're allowed to end your time slice early, and it doesn't get wasted. Like, we don't just do nothing for 2 time units because the kernel would have, got the exit, whatever it did, and it can now switch to something else and do something more useful. So in this case, our queue is P4, P2, P1. So now we would just schedule P4. It would execute for its 3 time units, and it's not done yet. It still has 1 time unit left. So our queue would look like P2, P1, P4. Now, each of these processes just has 1 time unit remaining, so we would just go in order. So P2, P1, P4. So any questions about that? Yep. Sorry?
Isn't it going to make our wait time really, really large? So, do we push them all to the end?
Yeah, so the question is, does our wait time get really long? And in this case, we do, because we essentially just had 1 time unit left on all of them. So we just had more work to do. But in this case, yeah, it would have been kind of unlucky, and we would have increased our waiting time. So for that, I guess, what is our waiting time? So, average waiting. So how long did process 1 wait around for? And here, I'll make it a bit easier. 16. There. So how long did process 1 wait around for? Yeah, 8. So process 1 waited around for 8. And why? Well, it ended here at 15. Here, I'll do this. Process 1 ended at 15. It started at 0. So it was there for 15 time units, and it took 7 to execute. So if we just subtract, it must have waited around for 8. Or you could count the boxes if you want. So process 2, well, where did it end? It ended at time 14. It came in at time 2. So it was there for a total of 12 time units. and it executed for 4. So it also waited around for 8. Then we have process 3. In this case, it waited around for 5 time units. So it finished at 10, and it started at 4. So it was there a total of 6, and it only executed for 1. So must have waited around for 5. Then last one we have is P4, which waited around for 7 time units. So it stopped at 16 and started at 5. So waited around for 11, and it wanted to run for 4. So math, it was 7. So if we do this, the average waiting time would have been 7. Then there's another time that we might care about. If you just care about, one of the things you might care about is the time it takes from when you first ask for it to run a single instruction. So maybe you get some output out of it, and that is called the response time. So that is generally something you care if it's like a graphical application where it's not going to do that much CPU work. You just want it scheduled at some time. So the response time is just the time it takes from when it first gets scheduled to when it first executes a single instruction. So in this case, for process 1, it's 0 because it started and ran instantly. And then for process 2, well, it only waited for 1 time unit. So it started at 2 and executed, it got its first time slice at time 3. So it only waited around for 1 time unit. The next process 3, well, it started at time 4 and didn't start executing until 9. So it waited around for 5. And then process 4, well, it got requested at 5 and didn't start executing until 10. So it waited around for 5. In this case, if we do the math, we get 2.75. And as someone brought up before, like switching between processes is not instant. So that's like a third thing we want to measure. So every time we switch processes, remember it's called a context switch. So we can count the number of those. So in this case, we just count how many times it switched from one process to another. So right here, it switched from process 1 to process 2. Then at time 6, it was process 2 to process 1. Then at time 9, it was process 1 to 3. Then 3 to 4. Then 4 to 2. Then 2 to 1. Then 1 to 4. So if we count out all of our blue markers there, we should get, what, 7? So in this case, we had 7 context switches. Our average waiting time was 7, and our average response time was 2.75. And then also one question you might have is like, oh, well, what about if a process arrives at the same time we throw something to the back of the line? So in that case, you want to always favor the new one because that will get its response time lower. The other one already had some response time, so it can just go to the uber back of the line, and you would just favor the new process. So we can do this example again. So here's all the answers for that. Oh, sorry. So average waiting time is the time until it finishes. Yeah, so average waiting time is time it starts, like how long did it wait from the time it starts to the time it finishes. And then response time is time it starts to when it first starts executing. So average waiting time, every process, the time every process takes from the time it starts to the time it finishes, and how long was it waiting during that whole time. Or basically, another way to think of it as waiting time is how long did it sit there idle doing nothing while something else got a turn, which is, if you go back to the analogy of your siblings, having to share something with your siblings, it's how long you didn't get to play with something. So that's another way to think of it. So we can do this again and be like, oh, okay, well, if that's their quantum length of 3, let's do it again with 1. And 1 This is just more of a pain because we'll just switch things over and over again. So all we'll change is the time slice. So let's go back. Oops. So now we have a quantum length of 1 single time unit. So as low as it can get just to see what happens. So same thing's going to happen. Time 0, we only have one process. That's P1. So we would choose that to execute just to make things easier. I'll just write the number here instead. And then at time 1, when it's done its time unit, which is only 1, well, it would get thrown to the back here. And then it's the only thing, so we just execute it again. And then P2 comes in, so we would favor that. So now our queue would look like P2, P1. Then we would execute process 2. Our queue would look like P1, P2. There's nothing new. Then we would execute 1. Now at time 4, we get a new friend. So it would be, P2, P3. And then the one that just run always goes to the extreme back of the line. So we'd get P1. So then we would schedule process 2. Our queue would look like P3, P1. And now we have a new friend. We have P4. And then we have P2, which just executed, so it's all the way to the back of the line. So now we have all our processes, and it's just going to go through this order. Hopefully you don't want me to write this queue every single time because that would get kind of painful. So it's always going to go 3, 1, 4, 2, 3, 1, 4, 2, 3, 1, 4, 2 until things are done. So in this case, 3 would execute. It's done at this point because it only wanted to execute for 1 anyways. So the rest of our queue would be 1, 4, 2. So then it's just going to go in this order until things just kind of end. So it would be 1, 4, 2, 1, 4, 2. And now at this point, process 2 is done because it only wanted to execute for 4 time units, which it's done. So now we only have, it's cycling between P1 and P4. So it would go 1, 4, 1, 4. And then it just kind of, they're all done at that point. So any questions about that? It's just more tedious, yeah.
This is a question about what you said before about ties.
Yeah.
So it's a tie between the total burst time of the new process versus the remaining time of the old process?
So this is just round robin. So our tie is a process arrives whenever one gets thrown out again. So that's kind of our tie here. Otherwise, we won't really have ties. If we have it, because we're just doing schedules on a single CPU, so we won't really have ties.
Okay.
So the only tie we have is process gets kicked out while a new one arrives.
So the new one will be first?
Yeah, we'd prefer the new one.
Okay.
Yep. Okay, so in this case, if we go get all of our numbers again, so average, So average waiting time, again, like the question, we count every process when it starts executing to when it's done. How long was it waiting around doing nothing for? And then divide that by however many processes there are. So process 1, how long was it waiting around for? Well, I should probably just do this again. 14. All right, that's all the important numbers. So process 1, it finished here at 15, and it started at 0. So 15 minus 0 is, it was there in existence for 15 time units, and it executed for 7 of those, so it must have waited around for 8. Then process 2 ended at 12, came in at 2, so it was there for a total of 10. It executed for 4, so it must have waited around for 6 of those 10 time units. All right, anyone quick math? how long did process 3 wait around for? Yeah. Yeah, 1. So it came in at 4, and it just waited 1 time unit, and then it got scheduled immediately. So 1. Then how about process 4? How long did that wait around for? So fished at 16, came in at 5. And again, it ran, it ran for 4. Anyone quick math, or we fall asleep? Seven, yay, yeah, 7. So it just waited around for 7 units. And then if we do this math, so I won't ask you this one, so you add those together, divide by 4 processes, then we get 5.5, which was, our waiting time went down. Hey, it was 7 before, it's 5.5 now. That's pretty good. What about the response time? So this one, thankfully, not much counting is involved. So P2 came in at 0, started executing at 0. So response time is time first comes in to when it first executed. How long is it waiting for? So it was waiting for 0. Now process 2, same thing. It came in at time 2, started executing right away. So that's another big old goose egg. Then next one was process 3. So it came in and it waited for 1 time unit. So it came in at 4, waited 1 round, and then it was scheduled next. So it waited around for 1. And then the next one, well, process 4 was the unluckiest of the bunch. It came in at 5 here. And it waited around for 1, 2 time units. So it waited around for 2. So if we take this, that's just 3 divided by 4, which we should know how to do. Whoops, I don't know how to do that. I wrote the 5 first. So 0.75. So in this time, our response time went down from 2.75 all the way to 0.75. So our response time got way better, and that kind of makes sense because we're swapping so fast. So the number that probably went up that isn't great is the number of context switches. Because so far, I've just kind of been assuming that everything is instant. So how many context switches did we have? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yikes. So in this case, we had 14 context switches, which if they weren't instant and they actually, if your context switch took, let's say, for argument's sake, it took 1 time unit, well, then realistically, this whole thing would have taken like 30 time units to execute instead of like the 16. So almost about half of that time would have just been switching between processes, which you can imagine is not that great. So you could do it again with 10 units, but at 10 units, that's longer than anything, so it becomes that first come, first serve. And you can see the number of context switches way down because we only switched 3 times. Our average waiting time actually improved a bit, but our response time went way up. So, and this is like the same case as first come, first serve without preemptions. So the round robin performance depends on the quantum length and the job length. So round robin typically has like low response time, good interactivity. So you want that for, applications you interact with. It's fair about the CPU, low average waiting time. And there's a caveat here when the job lengths vary. But the performance, really depends on that quantum length, and you have to, right, there's no correct answer. So there's extremes. At too high, it becomes first come, first serve. Too low, there's too many context switches, which is just overhead. That's not time your processes are actually executing for. And it also has another property that we didn't show in the examples that the average waiting time actually gets worse when the jobs have similar length. And that's just something you can simulate. So scheduling involves lots of trade-offs. We looked at a bunch of different algorithms, although some of them were probably somewhat intuitive. First come, first serve, shortest job first, shortest remaining time first, which is the same idea with preemptions, and then shortest remaining time first, which, that optimized the lowest waiting time. Then we had round robin, which kind of optimized fairness and response time, but our average waiting time gets sacrificed a bit. So before we end too, so we'll just go back to some process practice. So something like that looks a bit weird, and let's argue about what happens during this, and I'll try and explain it in a slightly different way too, and show that, hey, it's the return value of fork that's different, and like really try and illustrate this. So initially, let's assume we're just executing a process. It's starting. It's process 100, and it is currently at that line. Well, so far there's no fork, so everything is as you expect. So in process 100, it would execute this line, get some space for PID, and on the right here, I will write its variables and everything like that. So process 100 has a variable called PID. What's the value of PID? Anyone remember their C? Sorry? 101. So the value of PID now, it's just C. It's an uninitialized integer. So what's its value? 0 if you're lucky, undefined behavior otherwise. So it's garbage. So let's just make up a value just so we can keep track of it. So it'd just be garbage, some value. I'll assume it's 42 just for fun. Then when you fork, there is one process calls that fork. So in this case, process 100 calls fork, and that's what gets cloned. So process 100 would get complete cloned, and then a new process would pop up that is an exact clone. So process 100 would make process 101, and it would actually get that value of PID 42. So it is an exact clone. So what's going to happen is now the only difference is actually the return value of fork. So you can think of it this way. So it's a clone. At the time of the fork, the only difference between the processes is what fork returns. And then whatever you do with that return value, that's independent in the processes, and they can do whatever with it. So for process 100, fork returns 101 because that's the new one. And in process 101, fork returns 0 because it's the new child. So then at that point, you could choose either one of them to return first. So if 101 returns first, well then it would update its value of PID to the return value of fork, because that's what PID equals fork does. So its PID would be equal to 0. And then it is done executing that line. So PID 101 is here. Now, if process ID 100 goes along, well, it would just update its copy of PID with its return value of fork, which is completely different than the other one. So its return value of fork is 101 because that's the process ID of the new process. So now at this point, both processes would be on this line. Now they would, yeah, oh,
It's okay.
that's okay? Okay, so now either one could execute and would would call fork again. So let's say process ID, 101 calls fork. So process ID a new process would get made called 102. That's the exact copy. It would have PID equal to 0. And now we can argue that, hey, well, process 101 called fork. So in 101, it would get returned 102. And in process 102, it gets 0 returned. So now in this case, whatever one returns first, you can argue about it, but we have no defined order, so we'll assume 101 executes first. So it would update PID, its PID to 102, and then carry on, and then it's done. And then in process 102, it would just overwrite 0 with 0 again, and then be independent. So now each of them would finally call exit and exit. So now, okay, we're out of time, but hopefully this helps a little bit and we can finish it later too. All right, so just remember, pulling for you, we're all in this together.